is already in the normal form. So f of xy, or the function to produce the slope, is x plus y. And then the initial condition or the order pair would be 0, 1. Okay, we're gonna use more when we work on the process of the Euler's method. So first step, to find the explicit solution or to find the solution using the method that we went over in chapter 1 and chapter 2 for the first order, y prime equals x plus y. This one, you can see this as a linear form. So then to find the solution, we write it in the linear equation form. If you recall that, so y prime plus the px times y equals the f of x. And to find the solution using the linear equation method, you're gonna use the px and the fx into the solution process, solving solution process, right? Um, the solution of the linear is y equals 1 over mu multiplied by the integral mu times the f of x plus c. So what is the mu? Mu, or the integrating factor. Mu is e to the integral of the px with respect to x. For our case, the p is negative 1. Px equals negative 1. Then e to the negative 1 dx, or e to the negative x as a mu. Put in the formula. So 1 over e to the negative x integral e to the negative x multiplied by the f of x, which is the x, with respect to x, and then plus c. We see the product of the exponential and the x. So use the by parts. It's convenient to see this, that can be done using the tabular by parts. So find the derivative for the x, antiderivative for e to the negative x, 1 here, 0 here, antiderivative negative e to the negative x, e to the negative x, multiply cross way down, plus sign here, minus sign here, and 1 over e to the negative x is e to the x. Okay, just clean up a little at a time. So now the integral sign will be gone. Now we have negative e times e to the negative x minus e to the negative x plus c, or the solution y in the general form is negative x minus 1 plus c, right? C times e to the x, sorry. And then we just find the constant c using the initial condition. Initial condition is 0, 1, or x equals 0, y equals 1. So 1 equals 0 here, minus 1 plus c times e to the 0, which is c. Then we get the c value equals 2. Now the exact solution or the analytical solution, just put in. Back then we use the term the particular solution, right? So for the numerical method, we use this as the exact, or the function to produce the exact value of the solution. So the exact solution is in the form y equals negative x minus 1 plus 2 times e to the x. Okay, so we got the exact equation, and we're gonna set it aside. After we find the numerical solution, we're gonna subtract or find the difference of the exact solution and the approximation to compute the absolute error and the relative error. All right, so that's the first part. And then the next part, you are asked to use the Euler's method to obtain the four decimal approximation of y at zero point 0.2 using the step size h equals 0.1, and then put them together in the table that I put on the bottom of the page there. Okay, so from the differential equation that we have y prime equals x plus y, and initial point x0 equals 0, and y at 0 equals 1. This case, the step size is 0.1. Your goal or your target is to approximate y at 0.2. As you see, if x0 is 0, The next one, the x1 gonna be 0 plus 0.1 because plus the h, which is the step size. The next h is 0.1, and x2 gonna be 0.1 plus another 0.1 or 0.2. Or another way we can say we use the x0 plus 2 times h, which is 0.2. So the general formula to find the xn is x0 plus the h, which is the step size, multiplied by n. Now, the whole picture of number 2 here is to do 2 steps or 2 rounds of the Euler's method to get the approximation of y at 0.2. So back to the problem here. From the Euler's method, the formula is ym plus 1 equals yn plus the h or the step size times, I put the h first, so just yeah, it's easier to manage the numbers when we calculate, and multiply by the function at xn yn. Okay, from this formula we know the f xy is the x plus y, and the h is 0.1. So these two are two key things that we're going to use in the process to find y1, or for n equals 1. So that means x going to be x1 or 0.1. And at the end of the goal, we're going to get y1, which is y at x1, which is y at 0.1. Okay, or halfway through of the process. To get y1, we're going to use y0 plus the h, which is step size, multiplied by the function at x0, y0. So since x0, y0 is like 0 and 1, so on the side, I the, I'm telling you this is a tedious, and try not to put everything all in one main area. Kind of break it down and put on the side, work on the small pieces and bring it back into the formula. I'm going to use different color here. Since the x0 is 0 and y0 is 1, so the function at x0, y0, which is the function at 0, 1, go by the function x plus y. So going to be 0 plus 1 or 1. So then this portion will be replaced with the value 1. The h is replaced by 0.1, which is the step size. Y at 0 is 1. Now we get the y1 equals 1 plus 0.1 multiplied by 1, or we get 1.1. Okay. The problem asks to do 4 decimal places. You can leave as 1.1, or you can put 3 more zeros. It doesn't matter. So at this step, we get the order pair 0.1, comma 1.1 as the first approximation. Okay. And y1, again, y1 is y at 0.1. And the next step, we're going to do n equals 2. That means we're going to get to the point x2 or point 0, point 2. And then since the x1, y1 that we obtained, this is x1 and this is y1, we can use it to find the y2. So use the formula. Oops. Hang on a second. So then the y2 equals y1 plus h, or the step size, times the slope using the x1, y1. Okay. On the side, so the f of x1, y1, which is the f of 0.1, 1.1, or the sum of these two. So 0.1 plus 1.1, that give us 1.2. Now we're going to replace this portion by 1.2, this portion by 0.1, and the y1 from the previous calculation, which is 1.1. Then we get y2 as 1.1 plus 0.1 times 1.2, or 1.1 plus 0.12 put together to be 1.22 as the next approximation. And then the next order pair, now we get x2 comma y2 as 0.2 comma 1.22. And since our goal is to approximate y at 0.2, so y at 0.2 is approximately equal to 1.22 based on the step size s equals 0.1 using the Euler's method. Since we know the exact solution form as y equals negative x minus 1 plus 2 times e to the power x, x0, y equals 1, at x1, which is x equals 0.1, the y is negative 0.1 minus 1 plus 2 times e to the 0.1, and that gives us 1.1103 for 4 decimal places. x2 or the x equals 0.2, the y is negative 0.2 minus 1 plus 2 times e to the 0.2, or in the decimal form as 1.2428. Now we're gonna put our numbers in the same table to see the comparison between those two, like between the exact and the approximate. The approximate from Euler method is in this column as y at 0.1 equals 1.1. The actual or the exact value is 1.1103. The difference of these two numbers or the absolute error is 0.0103, gives the percent error as 9.28%. At x equals 0.2, y at 0.2 is 1.22 from the Euler's method, and the exact is 1.2428, gives the absolute error 0.0228, or the percent error in the form of 1.83%. We're going to see the plot of the exact solution curve and the numerical solution curve. For this website, it allows you to type in the function, which is the f of xy. For this example, our fxy is x plus y, and the initial point is 0, 1. The step size that we use is 0.1. And from the graph, you can see the plot of the curve in the solid one and the dotted curve. That's from the numerical solution. And the table show you the value as you keep going for n iterations. Our case, we are going to find the y at 0.2. From the calculation, you can see by the Euler's method, the y at 0.2 is 1.22. If you want to see the slope field together with this graph, so it's convenient to see the trajectory of the curve if you start at the initial point 0, comma 1. If you change the initial point, for example, to be negative 3, comma 4, so you would get different curve, and the behavior of the graph depends on the direction on the direction field or the segments that represent the slope at the point x, comma y.